There are two kinds of invariant curves in dynamical systems. There are periodic orbits that do something. And then there are these heteroclinic guys. Both are invariant. If you find them, everybody has to find them, given that that's intrinsic to dynamics. The problem with heteroclinic connections is that you know what they are. For example, if you're playing golf and there is a hump, and on top of the hump there is a little hole and you're trying to put it in there, then what you have to do is you have to hit your ball in such a way that it rolls and then it slows down. It slows down and it gets to the top. Now, if it's a little bit too fast, it'll just go. If it's a little bit too slow, it'll just come back. So it means it has to reach a state of zero velocity. It takes infinite time to do that. So, you know what these heteroclinic connections are, but in practice, we find them very hard to compute them, because if you compute them in time, they're infinite time. So what we do in practice, we use a little bit linearization, and then we start some distance away. If you start some distance away, velocity is not zero, so we can start moving slowly, but start moving, and then when we get to this area, we use analytic knowledge about the neighborhood, because we have linearization, and we stop it there, and we know that the rest would be an infinite time, straight line descent. So we produce some kind of finite time computations. Now, typically, these are orbits like all other orbits. When you're away from this very special equilibria, you don't even know that you're on a heteroclinic orbit. You're just moving through a system using your equations of motion. Meaning that here, if I compute some kind of estimate, some local stability, I will find out that this maybe has 7 unstable directions, 60,000 stable directions like every other orbit. What that means is when you come close to this, you're going very, very slowly, but you have 7 unstable directions. Now, having 7 unstable directions means that, roughly speaking, it's the multiplier to the time that I'm using. So it gets extremely unstable. So in the book, I give you examples for Lorentz that show you that you just cannot approach these points, because even if you'd go with accuracy of 10 to the minus 11, come close, you were approaching them forever, but you're unstable. They're beautiful because they should connect all the neighborhoods, so they should give us an alphabet saying if I'm here, I can go there, there. But I haven't figured out how to do it in practice. Periodic orbits are similar, but periodic orbits always whiz along, because you can never have a zero velocity on a periodic orbit, because if that happens, then you're actually on heteroclinic orbit, by definition. The point has zero velocity, that's it. So periodic orbit always moves around. You just have to go on. So this is an efficient way of exploring state space, periodic orbits. These guys seem to partition it nicely, seem perfect for establishing symbolic dynamics, but we don't have good computational methods for them. And if you find some, I would be very happy. And we need them in 60,000 dimensions. But even in 3, I would be happy. For me, it's a research question. Maybe the answer is in the literature, maybe the code exists. So this is not a course in mathematics. This is a course in, you have a research problem, and you want to solve it, and it has some equations. Solving it means, you compute it and you give predictions. So it's not enough to have a theorem. There's probably, all kinds of theorems that you can prove that if you count the unstable, stable directions of these 2 points, that generically you have a robust connection, etc. But what is it? And that we don't know how to do.